Good day, we're going to talk about the JFET small signal model, which is, as you can see, this is the Shockley's equation that was discussed in our previous topic. I sub d equal to I sub dss times 1 minus vgs over bp 1 tcc squared. So the change in drain current will result from a change in gate to source voltage that can be determined using the transconductance factor G sub M. So as you can see, this is the change in the drain current, which is equal to the transconductance times the change in the gate to source voltage. So transconductance factor, the trans is a terminology applied in the G sub M. It reveals that it establishes a relationship between an output and an input quantity. So the root word conductance was chosen because the G sub M is determined by a current to voltage ratio, similar to the ratio defines in the conductance of a resistor, which is the G conductance is just equal to the reciprocal of the resistance, or it is equal to the current divided by the voltage. So solving for the transconductance G sub M, so this will be from this equation, this will be change of I sub d divided by change of V sub gs. So as you can see, so if you say change in id as with respect to change of the gate to source voltage, so it will be derivative. So it will be the derivative of I sub d with respect to derivative of b sub gs. So if you take the derivative of the function with respect to the gate to source voltage, so this will be so therefore this will be the derivative of the drain current with respect to vgs. So this will be id. So substitute this equation. So times 1 minus v g sub s divided by vp quantity squared. So we take the derivative. So this will be um, so the derivative of this function is equal to 2 idss. So from your differential calculus class, so 1 minus vgs over vp times the derivative of this term. So this will be this is derivative of constant negative. So derivative of this one is 1 over vp, and then simplify. So this will be 2 idss the minus 1 over vp. So this will be negative 2 idss divided by vp times negative times 1 minus vgs over vp. So therefore, this is the transconductance formula G sub M. So this will be, so what we want to have is the magnitude only of the pinch of voltage. So therefore, this will be 2 idss. So this will be the magnitude only of the pinch of voltage. So we don't need the sign. So this will be 1 minus vgs over vp. So this is the transconductance formula. So G sub M equal to 2 IDCS divided by the magnitude of the pinch of voltage V sub P times 1 minus VGS over VP. So if you let VGS, so if you let VGS, which is equal to 0, so what we're going to have is so if you substitute this VGS to the formula divided by BP, so 1 minus 0 over BP, so what we're going to calculate is GM sub 0. So GM sub 0 is the maximum value of the transconductance. So it happens when the VGS is equal to 0. So this is where the maximum transconductance occur. So VP. So this is the maximum transconductance if VGS is equal to 0 volts. So this is the formula for the transconductance. So you can find the maximum transconductance if VGS is equal to 0. So let's go to the JFET input impedance. So unlike the BGT input impedance, so the input impedance of bipolar junction transistor, it depends on uh, the component R sub B. But in JFET, normally, the internal input impedance of JFET is quite larger compared to a BGT. So as you can see, ideally, JFET input impedance is almost equal to infinite. But in actual JFET, usually it ranges among 1000 mega ohms, typical, and MOSFET and MESFETs has just a range of 10 to the 12 ohms to 10 to the 15 ohms. So compared to the BGT, JFET is superior in terms with the input impedance. So the higher the input impedance of an amplifier, the more efficient yung amplifier would be. So gamay ra yang. So it will lessen the noise and you can achieve the maximum power transfer of the input signal to your amplifier. So the JFET output impedance Z out. So it usually in the data sheet it symbolizes. So its symbol is J sub OS, or you can find Y sub OS, and it has an um, unit with microsiemens. So YOS is an admittance equivalent circuit where the O signifying an output network and the S is the terminal or the source to which it attached in the model. So usually JFET J sub OS has a range of 10 microsiemens to 50 microsiemens, or it ranges from 20 kilo ohm to 100 kilo ohm. No? So this is the formula for the output impedance of a JFET. So if you find G sub OS or Y sub OS in a JFET's uh, data sheet, so you just take the reciprocal, no, and you can find the R sub D, internal resistance of the JFET. You just take the reciprocal of J sub OS or Y sub OS, and you can find the R sub D of the JFET or the output impedance. So this is the JFET is equivalent. As you can see, the R sub D is that's just eternal resistance. So usually only yung output impedance. So as you can see, we have an input voltage VGS, and we have a current source, the transconductance times the VGS. So this is the AC equivalent circuit of a JFET. So okay, let's go to the fixed bias configuration. So applying the JFET AC equivalent model to this configuration, as you can see in your electronics 1, A fixed bias configuration of a JFET has a voltage source, DC source, VGG, and then there's a RG resistor, and it has the drain resistor. So this is a fixed bias configuration. So applying the analysis, AC analysis, same with the BGT model, AC equivalent. No? In order to analyze this configuration in AC analysis, we should short all DC sources and um, short all capacitor and ground all DC sources. So as you can see, can VDD, so it will be connected to the ground. The VGG will also be connected to the ground, and the capacitors will be shorted. So by applying those steps, so we have this JFET AC equivalent circuit. As you can see, RG now is connected to the ground, and then the R sub D is also connected to the ground terminal. So applying the AC equivalent, we have the input voltage V sub GS and the current source, and also we apply the internal resistance of the JFET R sub D. So the same with the BGT AC equivalent circuit or the RL model. So we're going to find the most important parameters of this analysis, which is equal to, so important parameters for an amplifier is the input impedance, the output impedance, and the voltage gain. So ZI, ZO, and the voltage gain. So as you can see in this analysis, the input impedance is just equal to the ZI, input resistor, which is equal to RG. So usually R sub G has a very large value, so therefore the ZI, input impedance of a JFET, is larger compared to the input impedance of BGT. So how about the Z out? So Z out is just equal to, as you can see, the output side will be R sub D parallel with the capital R sub D, or if R sub D is 10 times greater RD, so you can assume that Z out is just equal to RD. So if this parameter, the internal resistance of the JFET R sub D, is greater than or equal to 10 times RD. So the last one is the voltage gain. So we're going to calculate the voltage gain. So as you can see in this figure, in the output side, so we can find the output voltage, which is equal to so if you use the Ohm's law, so since the current is in this direction, so it should be negative. So current times the resistance, so the overall current of the output side is equal to GM times the equivalent resistance of this resistor and this resistor. So therefore, current GM VGS times the resistance R sub D parallel with capital R sub D. And also, as we all know, that since this VGS is nakaparallel siya sa VI, so therefore, our VGS is our input voltage. So substitute this one to this equation. So V out is equal to negative GM VI times R sub D parallel with capital R sub D. So since the voltage gain is just equal to V over VI, so A sub B is equal to V over VI equal to negative GM R sub D parallel R sub D. So as you can see, this is the voltage gain of a fixed bias JFET fixed bias configuration. But if RD is 10 times greater the capital RD, so we can assume that our voltage gain is equal to negative GM RD. So to simplify the formula, so they're the same. So if uh, this value is 10 times greater or equal to R sub D, so pwede na to i-neglect ni. We can neglect this one. And it will be voltage gain now is equal to negative GM RD. So let's have an example. So we have a fixed bias configuration. So determine, so we have a DCS 10 milliamps, BP negative 8, and we have this admittance YOS equal to 40 microsiemens. So 2K R sub D, 1 mega ohm ang R sub G, and we have the DC source of 2 volts. Determine GM, transconductance, R sub D, the input impedance, Z out, the voltage gain, and also the voltage gain ignoring the effects of RD. So we're going to compare letter E and letter F if obviously significant difference if we neglect R sub D. So the transconductance, we can calculate this one. As you can see from our previous discussion. So GM formula is that this is what we calculated earlier. GM is equal to this was formula. So therefore this will be 2 IDSS divided by magnitude of absolute value of VP 1 minus PGS over BP. So in order to calculate transconductance, we need to find the gate to source voltage first, and we need the DC analysis. So get the formula ni. So VGS is Nadrino. So this is the gate. This is the source. So in our electronics 1, we discussed this topic where VGS is just equal to the negative VGG. Where the VGG is equal to 2 volts. So therefore VGS is equal to negative 2 volts. So we can now calculate the transconductance. So 2 times 10 milliamps divided by 8 times 1 minus negative 2 over VP is negative 8. So therefore this is 20 milliamps divide 8, and then 1 minus. So use your calculator. So this is equal to so the transconductance is equal to 1.875. Unit is millisiemens. So don't forget for the unit, it's very important. So GM 0.875 millisiemens. So how about RD? So RD is just the reciprocal, no? 1 over 40 micro. So therefore this is so it's 25k units. So this is 25 kilo ohms. So R sub D is equal to negative 25 kilo ohms. So how about letter C, the input impedance? Input impedance is just equal to Rg, which is equal to 1 mega ohm. So how about letter D, the output impedance? So the output impedance is just equal to um, so if you look at the output, this one, so it's just the parallel between the small r and the capital R sub D resistances. So therefore, this will be, so R sub D is 25 kilo ohms parallel with 2K. So Z out is, so Z out is equal to 1.85. 1.85 kilo ohms, and then the voltage gain is negative GM. So the transconductance is equal to negative 1.875 milli times parallel in duha. This is 2 kilo ohms. So therefore, this is negative 1.8 times. So therefore, voltage gain is equal to negative 3.47. So negative 3.47. So this is the voltage gain with, we didn't ignore the R sub D. So how about if we ignore the internal resistance of the JFET? So F voltage gain is equal to negative GM R sub D, negative 1.875 milli times 2K. So voltage gain is equal to negative 3.75. So as you can see, with the effects of R sub D, we've calculated the voltage is equal to negative 3.47. But if we neglect internal resistance, so it is negative 3.75. So if you compare these two values, this is more accurate compared to this one because we've neglected the internal resistance of the JFET. But as you can see, the voltage gain is different, is not that significant. So, dollar lang value. So that's it.